Hi. In this presentation, we will look into the operation of the finite state machine that makes up the test access port controller. After watching this presentation, you should be able to explain how this sequence of zeros and ones driven to TMS will control the operation of the embedded test infrastructure. The state diagram of the TAP controller comprises 16 states as shown here. We start from the test logic reset state, which sets all boundary scan cells to transparent mode. In other words, all the pins will be connected to the core logic, and the circuit will operate normally in this state. Notice also that test logic reset causes the bypass instruction to be loaded into the instruction register, so bringing the TAP controller to test logic reset has a similar effect to powering up the board. You may recall that we have to start by driving an appropriate sequence of zeros and ones to TMS in order to select the lower input of the data instruction multiplexer, since this mode is required to shift in the first instruction, and also to shift out the 0-1 patterns that will check the integrity of the boundary scan chain. So this will happen in the shift instruction register state. So we have to start by driving a 0 to TMS and a rising edge to the test clock in order to go from test logic reset into run test idle. Notice that the boundary scan cells continue to operate in transparent mode as shown here on top. Next, we drive a 1 to TMS in order to go from run test idle to select data register scan, and then another 1 to go from select data register scan to select instruction register scan, and then a 0 to go from select instruction register scan to capture instruction register. Nothing has yet changed in the boundary scan cells, but this is actually the moment when all the instruction registers in the boundary scan devices in the board will capture the pattern containing 0, 1 in the bits closest to TDO. We are now ready to shift in the first instruction, so we will drive a 0 to TMS in order to move from capture instruction register to shift instruction register. This is the moment when the data instruction multiplexer switches to its lower input as shown here in the slide. We will remain in this mode while TMS is held at 0 for as many test clock cycles as the number of bits in the instruction register. However, in the very last test clock cycle, TMS must be driven to 1 so as to move out of shift instruction register as the last bit of the instruction code is shifted in. We then move from shift instruction register to exit 1 instruction register, and the new instruction has been shifted into the instruction register and is ready to be loaded into its output stage and driven to the instruction decoder. Notice that the boundary scan cells are still in transparent mode since the current instruction is yet the same that was present when we initiated this process, but that's about to change. By driving a 1 to TMS, we will move from exit 1 instruction register to update instruction register. And that's when the new instruction is finally seen by the rest of the test logic infrastructure. And consequently, the operating mode of the boundary scan cells will change, as shown here for the case of the external test instruction. All boundary scan cells will in that case switch to test mode, and the pins will disconnect from the core logic. If we now want to shift in any given test vector, we must go from update instruction register into select data register scan, and from there continue on to shift data register. So from select data register scan, we must drive TMS to 0 in order to move to capture data register, where all the multiplexers in the capture shift stage will select the parallel input of the boundary scan cells as shown up on the left. The parallel outputs will hold the value coming from the latch stage, and we might actually have preloaded an initial test pattern by starting with the preload instruction instead of external tests. So at the next rising edge of the test clock, all the flip-flops in the capture shift stages will capture the value coming from the parallel input of the cell, and we will move into the shift data register state if TMS is driven to 0. The capture shift stage multiplexers will now select the lower input as shown here on the top left, since we are about to shift in a new test vector. We must remain in shift data register for as many test clock cycles as the total number of boundary scan cells. And again, we must drive TMS to 1 in the very last test clock cycle, so as to move out of shift data register and into exit 1 data register. The new test vector has been shifted in, but the outputs of the boundary scan cells have not yet been updated. By setting TMS to 1, we can now move out of exit 1 data register and into update data register to bringing the new values to the outputs of the boundary scan cells. Most of the test events happen at the rising edge of the test clock, but the outputs of the cells, be it the instruction register or the boundary scan register, will be updated at the falling edge of the test clock in the update state. We can now repeat this process as many times as the number of test vectors. And notice that by the next time that we pass through the capture data register state, the input stage of the boundary scan cells will capture the responses to the test vector that we have just loaded now. And that's all. Thanks for your attention.